All right, gang, I wanted to talk through a couple of the problems from today. So here we go. So of course our goal, our learning target is to be able to solve these separable differential equations even when they're in a real world context. All right. So the baby bird, I just wanted to talk through, some of the solutions there, the A, B, and C parts. So this is the original problem that you were given yesterday. So let's kind of go through some of this. Okay, the first question, it was asking, is the baby bird gaining weight faster when it weighs 40 grams or when it weighs 70 grams? Well, we can use the differential equation because that gives the rate of change of the baby bird's weight as it relates to time. So we can just take the 40 and the 70 and actually just plug them right into that differential equation. And when we plug them in, we get 12, and we get 12 when the baby bird's at 40 grams, and then we get 6 when the baby bird's at 70 grams. And so we can tell that it's definitely gaining weight faster right in the beginning. Doesn't that make sense that the baby would be gaining weight faster, when it's a little bit younger, in the beginning than as it gets older? Take note too of the notation. So this is a way to show that you're plugging something into the derivative. So dB dt, and it has this little bracket, and then you can put whatever you're plugging in near the bottom there. So b equals 40. Okay, so kind of going back, it's just going, and that's being plugged into this derivative here. All right, that's part A. Part B, it says, what was the question again? Part B, it says, go ahead and try to find the second derivative of b with respect to t. That's what that notation is. And so we want to use that and try to explain why this graph, doesn't really, this graph right here, why it doesn't resemble the situation, okay? So what we do is we take the derivative, the first derivative, and so actually I'll just kind of show you what they have here. They have this work, they have the negative 1/5 dB dt, and then they take the derivative again and they get this, and then they simplify it and they get negative 1/25 parentheses 100 minus b. But what I'd like to do is do that one just from the beginning, because when I first saw this, it kind of looked funky to me. So I want to go back to what the start is. So dB dt equals 1/5. Okay, so I'm going to write that. So I'm going to say dB dt equals 1/5. And then it was, what again? It was 100 minus b. Okay, so I'm supposed to find the second derivative. Just for me, I think it's easier to see this as the first derivative still. So let's just kind of distribute this. So if we do, that would be, would you agree that would be 20 minus 1/5 b, just if I distribute that 1/5. Now I'm ready to find the second derivative. And when you find the second derivative, just want to show you where that notation comes from, because you're finding d dt of both sides, dB dt of both sides. And so that's why you would have two of the, oh, booger, I messed that up already. Oh, booger. You're finding d dt, you're finding the derivative, with respect to t. And so that's why when you have the d times the d, that would get you the d squared, and then b, and then on the bottom you've got two of the t's. So it'd be dt squared. That's kind of just shows you a little bit of the notation. Okay, so now let's find the derivative. On the right-hand side, what you do is, of course, you're going to say the derivative would be negative 1/5, because you're carrying that along for the ride. And then think of the capital B, just like whenever we came across a y, we'd always say y prime or dy dt. Well, now we're coming across a capital B, and so then we would say the derivative of that. So we would say dB dt. So that would be the second derivative. The only thing is we don't really want the second derivative in terms of the first derivative. So then we just replace that dB dt with what we know it to be, and see this here is the dB dt. So then we just replace it, And so we say this would be 1/5 and then 100 minus b. And then we can simplify it a little bit like they did. So they have the -1 over 25 and then 100 minus b. So this is where they're getting that second derivative. Okay. Now part C is our solving, so our separating and solving, knowing the point the bird is originally at 20 grams. All right. So this is where we separate and solve. And so I think they did an okay job doing this. So I'll just kind of run through some of the steps and then fill in where I think they skipped a step or two. So first we have this, and so you can tell that they divided by the 100 minus b, so that's not too crazy. And then they multiplied by the dt, so that's where they got, this step here. Then what they did was they integrated. So they separated, they integrated. Remember that little negative in front for the natural log whenever this turns out to be negative right there. And then, so that part looks decent. And then what they did was they said, hey, you know what? We don't even need the absolute value bars because this baby bird is going to be between 20 and 100. And if you plug in 20 to 100 in here, you're not ever going to have natural log of a negative amount. So they said, let's just take away the absolute value bars. And for now on, let's just write natural log of 100 minus b. So that's what they did. And so then the next step, as you know, is to plug in the point 0, 20. So that's what they did right here. So they plugged in 0 for the time, and then which is right here. They plugged in 0 for the time, and then they plugged in the 20 for the b, which again is, right here. So they solved this. They got the c. Now this part is where I think they sort of skipped, to get to this 100. So let's go ahead and plug in our constant. Let's plug it in to this step right here. So this would be negative natural log, but I'm going to not use the absolute value bars because we already determined we're not going to need them. Okay, and then I'm going to have 1/5 t, and then I'm going to use that c that they found, we found. Now on this one, this is where you have this negative sign in front, so I would multiply by -1 to move it over to the other side. So multiply by -1, and then that would be natural log 100 minus b equals -1/5 t, and then plus natural log of 80. This is where we would exponentiate, so that would be e raised to each side. So 100 minus b equals e, and then of course this whole left side just as it is, really. Okay, and then that property that we utilize here, and so we write, let's see, so wondered if I wanted to show that step or if I'll just show it again on the next step. So this e to the natural log will cancel out, so I'll wait, maybe show it later. So that'll be 80, and then it'll be e to the -1/5 t, and then on this side it's 100 minus b, and then we can just try to solve for b. So we're going to subtract the 100, so 80 e to the -1/5 t, and then minus the 100, and then multiply by -1. So we could maybe switch the order a little bit. So we could say positive 100 first, and then minus 80, and then e to the -1/5 t. And that's b of t, so it's a function b of t. So that's where they get all that. So hopefully that is a little bit better. All right, so now let's talk about the waste management, type of 1, the landfill. So I typically have a problem like this on the celebration, so this would be a nice one to understand. So let's run through a few steps. So part A, it says write the line tangent to the graph, and so we know to write a tangent line, we just need a slope and we need a point. So we have a slope. The slope is the derivative, so we just need to actually plug in, something for the w to get what the slope is at that particular amount of tons. And then we have a point. They gave us the point at a time of 0. Let's see. It was, what was the amount of tons? Oh yeah, it was 1,400 tons. So at a time of 0, it was 1,400 tons. So good, that's our starting amount. So let's go ahead and plug that in. So you see here, we have the 1,400 just plugged in for the W right there. And then that gives you the 44 tons per year. And so that's your slope. That's your rate of change or your slope. And then we use the point 0, 1,400 in the point slope form. And so we would do W, again, W is like your Y. So W minus 1,400 equals 44, and then parentheses T minus 0. And then you don't need the minus 0, so you can just say 44T. And then add the 1,400 over, and then you get this really good tangent line approximation, right? And then you can utilize that to predict, like, hey, how much waste are you going to have 3 months later? And 3 months is 1/4 of a year. So you plug 1/4 of a year in for the T, and you get 1,411 tons. So it gives you a pretty good approximation as to how much you're going to have in the landfill at the 3-month mark. All right. And then the next question, it said, what about, is this going to be an overestimate or an underestimate? So what we can do is utilize the second derivative just to see, or find the second derivative, and then see if that can help us to determine whether the linear approximation is an overestimate or an underestimate. So to find the second derivative, we do the same thing we did on the baby bird problem. So at least I do like to do that. So I would distribute the 125 first, 1 over 25, and you get 1 over 25W minus 12. And then if you think about taking the derivative of that, you would, of course, carry the 1 over 25 along for the ride, and then take the derivative of W with respect to time, so that would be dW dt. And then you can replace the dW dt with what you know that it is, which is the original here, 1 over 25, parentheses W minus 300, so you replace it with that. And then you can simplify it a little bit, just multiply those two together. So that's a good second derivative. Now you can see if it's going to be concave up or concave down. So if you were to plug in the 1,400 tons that we have of waste initially, you can tell when you plug it in that it turns out to be a positive number. And we know that when we have a second derivative that's a positive number, we know that it's concave up. So then we think about, okay, how does this logic help us to determine whether the linear approximation would be an overestimate or an underestimate? Well, we know at this point, if we know that it's concave up, I like to draw a graph like this and say, hey, if this is concave up, the graph would be going up. And if I did a linear approximation at that spot, then I know my linear approximation would not be high enough. It would be an underestimate. So that's the logic of how we can use concavity to determine whether a linear estimate is, or a linear approximation is, an overestimate or underestimate. Of course, if it was concave down and we did a linear approximation, then we'd say, oh gosh, we're going to be way over what it actually is because it's concave down. Okay. All right, so let me erase that little piece. And then the last part is just the separating and the solving. So hopefully you're feeling a little bit better about this part, even as it applies to real world problems. So we separate, we multiply by dt, separate and integrate. We divide by W minus 300. This one turns out pretty nice. And then we plug in the point that we know. So we have 0 and 1,400 that we can plug in. And we get natural log of 1,100 is the C. We plug that in right there for the C. And then we exponentiate. And we get W minus 300 in absolute value bars equals e to the 1 over 25t plus natural log 1100. And then we can use that little property. So I think I mentioned I was going to use that little property a little more here. So this is where we say, hey, this is the same thing as e to the 1 over 25t times e to the natural log of 1100. And then we know that e to the natural log of 1100 would undo each other. So we'd be left with just 1100. And then we can do the plus and minus to get rid of the absolute value bars. And then we can decide which we really need. Do we want the plus or do we want the minus? And so we have to make sure that when we plug in a 0 for the time, that it actually turns out to be 1400. And you can tell if you put a 0 in for the t, that it would make that 1, this part 1, e to the 0 would be 1. And then this would be 300 plus 1100, which would be 1400. So that would be the correct one. We want it to be plus. And then now, once we have a really good function, then we can go ahead and use it to predict how much waste we're going to have at the 3-month mark. And so we plug in 1/4, and super hard to see, but it's going to be, 1 over 25, 1 over 25, that is hard to see, times 1/4. Ooh, that's ugly. Anyway, better that I just state it. So 1 over 25 times 1/4, because we're just plugging it in, is, on the calculator, it turns out to be about 1411.055 tons. So it was really close to what the linear approximation was, but you can see that this is more, and so the last one was an underestimate, as we guessed from the concavity, or as we knew from the concavity. All right, so hopefully that helps you out. Good luck.